good afternoon. Let's go ahead and get started with our Chem 400 lecture for today. Where we left off was we were talking about energies of bonds. And we'd just gone through something called bond dissociation energies. And what we found out was that if there is a bond between two carbons, wherever that carbon-carbon bond is, it has roughly the same energy, whether it's in propane, whether it's in cyclohexane, wherever it is. And that's not perfect, but it actually does pretty well and is about plus or minus 10% or better, which is pretty good. And those are bond energies for covalent compounds. There's only one other type of compound in Chem 400. Those are called ionic compounds. Ionic compounds, the way to estimate the strength of an ionic bond in an ionic compound is using what's called the crystal lattice energy. And in fact, the way to determine the crystal lattice energy, and so let me attempt to be clear here for a second. So the crystal lattice energy is an attempt to determine the energy associated with an ionic bond, or the strength of that ionic bond. So that's why we're doing this thing called the crystal lattice energy. Now, what I'm about to do for you is what's called a Born-Haber cycle. It's right here. I know it's a little hard to see. Hopefully it's easier to see on your handout. And in a Born-Haber cycle, you're adding up several reactions using what's called Hess's law from chapter 6. And the reactions always add up to what's called a delta HF reaction. And delta HF from chapter 6 is the change in the enthalpy of formation under standard state conditions. It is, so formation means that we're forming something. And in this particular case, since we're going to be determining the crystal lattice energy, delta H sub CLE for sodium chloride, the thing that we will be forming is sodium chloride. And for those of you who had discussion this morning, you've seen this before, but for those of you who did not, so we're covering all of it. A formation reaction for whatever is being formed means that this thing is the product. And it has a 1 coefficient. Always true. And that's why on chapter 6 homework, we did write a delta H formation reaction, and it was the same subtleties. If you remember, the reactants were the lowest energy forms of each element. Those are reflected in the colors of the elements on the periodic table. Sodium has black letters. That means it's a solid. It is not one of the diatomic elements, and therefore we write it just as an atom in its solid phase. Chlorine, on the other hand, has as its lowest energy form at room temperature chlorine gas. It is diatomic. And to balance this reaction for delta H formation with a 1 right here, always true, what coefficient do we need here? 1/2. Thank you. And we've said for a little while, certainly since chapter 6, that half or fractional coefficients are okay. When you're thinking of reactions in terms of moles, there's still no such thing as half a molecule of Cl2, but there certainly is half a mole. So this is the basis, or one of the basis species for this reaction. This line is an equal sign. And the rest of the lines are just to help me organize things. But what's going to happen is we're going to put a bunch of reactions up here. We're going to add them up via Hess's law to make the reaction down here. Just like in chapter 6, when we add up the energies of these reactions, it will add up to the total of whatever this one is. Okay, so next thing we're going to do is, for each of the substances that we have here, we're going to start with them And the process is going to be to turn each of these into gaseous ions. So I'll make a little note here. Gaseous ion. And I'll show you what that means. And when I do it, you'll see that these are a bunch of reactions that should be familiar. As we turn, so first thing we're going to do is we're going to turn solid sodium into a gas phase. This is what's called a sublimation reaction. And sublimation reactions, well, we've seen specifically the sublimation reaction for carbon dioxide. Carbon dioxide solid goes to carbon dioxide gas. And this is the same thing for sodium. And in a problem like this, I would have to give you this number. And it is 108 kilojoules per mole. And this number, as you turn a solid into a gas, that is always an endothermic process. And as an endothermic process, it will always be take energy to do that. Now once I turn it into a gas, then I will turn it into an ion, a gaseous ion. By writing an ionization energy reaction. Again, this is a reaction we've seen before, so there's actually nothing new here as far as the reaction goes. Well, the crystal lattice energy reaction was new last lecture, but everything else we've seen before, including Hess's law, so it's like an application of all these things we've learned. And we'll write out the ionization energy, or the first ionization energy for sodium. The value for that, 496. I'll omit the units since the units are up here at the top, kilojoules per mole. Said, side note, all ionization energies are endothermic as well. Taking an electron and removing it from any of these atoms on this periodic table is an endothermic process. We have trends in them, of course. As we go to the left and as we go down on the periodic table, the ionization energy decreases. Any questions so far? Because we're finished with sodium, and we're going to do the same thing again, except now for chlorine. It'll be a little different because chlorine, we're starting with a molecule, and here we had an atom. And we already have a gas. So there's nothing to do gas-wise. What we're going to do is we're going to take this molecule and break it into two atoms. And you can either write them as two separate atoms or use a 2 coefficient here. Either way is fine with me. This process we introduced last lecture. We called it the bond dissociation energy. And we said, and as you work through homework 9, you're seeing the bond dissociation energies are on one of the tables on your conversion and equation sheet. You always have the bond dissociation energies. And for this particular bond, it is 243 kilojoules per mole. That means to break 1 mole of chlorine gas into these atoms takes 243 kilojoules. Well, now we're going to turn chlorine gas into a gaseous ion. One note, all of the ions that we're making have the proper charges that you're used to. Note that sodium becomes sodium plus, chlorine will become chlorine minus, what we're used to. It is new that they're gases. Yeah, true. But what's not new is the process of turning it into an ion. This is going to be what's called the electron affinity reaction. It is where you add an electron to a gaseous atom and create Cl minus. and that is called delta H, electron affinity 1, EA1. And if you recall from, I think it was either 1 or 2 lectures ago, I did not ask you to remember any trends in electron affinity. However, and that's because I have a hard time remembering them myself. Fair enough. However, I will point out that in this particular case, we are creating a noble gas core of electrons. And so perhaps it is not surprising that that is an exothermic number, that is, or an exothermic process, because we know that noble gas cores of electrons are particularly stable, and forming them lowers the energy. So we may not, I wouldn't say we necessarily know how to predict this or not. It's more complicated, but perhaps we're not too surprised. And you don't have to remember any trends in electron affinity. All right? Let me see here. Okay, so now we've got gaseous chloride ions, gaseous sodium ions. Now it's time for the crystal lattice energy reaction. Crystal lattice energy, again, I know we just introduced this last Wednesday, was it? And we haven't seen each other since then. But a crystal lattice energy is the process of taking positive and negative ions and bringing them together to form the solid. Bringing them together to form the solid. That's called delta H CLE for crystal lattice energy. And it is the one reaction that we don't know so far, and therefore we can solve for it. So this is the entire setup. I'll do a couple other things to it. If I can find my red pen. In true Hess's law form, most of the things that are on each side, most of the things are on both sides and will therefore cancel out. The only things that should not cancel are the things that end up in our summation reaction. Sodium solid will not cancel, but sodium gas does. Sodium ion gas does cancel. Chlorine 2, well, something's up because I have half Cl2 down here and just one Cl2 there. However, there's a couple things going on because I have 2 Cls and only 1 here. Anyway, the next step is to figure out that this reaction has to be multiplied times 1/2 to get it to cancel out. And if the reaction is multiplied times half, so is the delta H value. And that is how you get the right answer, is you find all the halves. Sometimes it's a half, sometimes there's a 2. There's always some factor that's in there that you have to figure out. But when I do that, now my half Cl2 gas matches my reaction, my summation reaction. I have one of these because it's 2 times half, and I have one of them there. Because really it's just one. Let's see. And I have 1 electron. I have 1 electron. Even the electrons cancel. And finally I have one other thing. My Cl minus gases. So the only thing I have left is the thing that comes down at the bottom. Sorry, I have to step out. Ah, it's gorgeous. I mean, look at that. All those things that cancel. It's like it tells a story. I don't know what that story is. But that's yeah. Any questions? If not, I'll say a couple things about this. One, we're not done because we're trying to determine X right here, and in true Hess's law of fashion, take this plus half that, plus this plus x, and set it equal to whatever this number is. I forgot to give you this number. Let me put that number in now. Oop, I'll put it in black to color coordinate it. The delta H formation, minus 411 kilojoules per mole. All right, now I'll go back to red. So all of these equals that. I'll write that in this space here. I should look at my notes more often because I think this was supposed to be up here and this was supposed to be down there, but hopefully that's okay. And then you solve for x. When you solve for x, the first thing I will point out to you is that crystal lattice energies are all negative. Because when you take a positive anything and a negative anything and you bring them together, they will lower their energy. That means this is always an exothermic process. Anyway, when you solve for x, that will be the crystal lattice energy, and it is equal to minus 788 kilojoules per mole. The book, by the way, TRO, for those of you who have it, or any book usually, has a very elegant diagram of this entire process in which it turns this process into the largest reaction energy diagram you've ever seen. And it's actually pretty useful to look at, I will say. But in the end, when it comes down to what you're going to see on your exam, it's going to be more like this. So I've decided to show it to you this way. Anyway, so the textbook can be a good resource for Born-Haber cycles. Any questions about this process? So my emphasis would be there's really nothing new here. I guess, I was going to say a couple things. Let's see. So almost all of these values I have to give to you, except for the bond dissociation energy. That's on your conversion equation sheet. Delta HF values. There's a whole table of delta HF values on your conversion equation sheet as well. And so one of the tricky things about this can be that you might have to look some of the numbers up, but you have them. And so if you see a problem like this on your homework or exam, and some of the numbers are missing, you may have to know to go look for them. And then oftentimes when I put this on homework or an exam, I say, please write out all the reactions and show how everything cancels out. And so I will, sometimes I will make you do exactly this to get full credit. There's a companion problem right here. I encourage you to do it before your third exam at this point and to help you do homework number 9 and practice homework number 9. How many people got an email from me about homework number 9? Raise your hand. How many people did not? If you did not, then this will be very helpful to know. So homework 9 answer key has been posted. I posted it early because of my lack of office hours this week. And homework 9 will only be graded on completeness, meaning since you have the key, use it as best you can to learn the material, but in the end, make sure you get your 10 points by completing it. Please feel free, in fact, please don't copy it. Please feel free not to copy it and put it in your own words, your own format. I realize it will look very similar to mine, but I encourage you to put in thinking, critical thinking. Anyway. So that's the update on homework 9. It is still due this coming Wednesday. Born-Haber cycle. Ta-da. Nothing on my sleeve right now, that's for sure. All right. So there's a companion problem. Ooh. We'll skip the companion problem, leave it. Remember, companion problems have their answers on the Chem 400 website. Now I'm going to talk about trends in crystal lattice energy. Trends in crystal lattice energy follow what's called Coulomb's law. Coulomb's law says that the energy between different charges, E is energy, is equal to 1 over 4 pi epsilon naught. And we don't have to know this term, but that is what Coulomb's law says. The next term over here is going to be lowercase q1 times q2 over r. And it's actually q1 and q2 are charges. R is the distance between those two charges. Distance between charges. I think is there a chapter 9 homework about Coulomb's law? If not, there should be. But, all right, so, okay, so this is under trends in crystal lattice energy. The trend is that crystal lattice energy, delta H CLE, crystal lattice energy, increases as the product of the charges increases. Crystal lattice energy increases as the product of the charges increases. And this comes directly from Coulomb's law. It says that the energy of the two charges is equal to these constants times Q1 times Q2. So product just means multiply, right? Q1 times Q2. And as an example of that, I will give you the crystal lattice energy for sodium fluoride and calcium oxide. So here's the two compounds. I'm going to write their crystal lattice energies underneath them in kilojoules per mole. Minus 910 kilojoules per mole for sodium fluoride. Minus 3,414 for calcium oxide. Now I'm going to go back in and add their charges. Sodium fluoride is what I like to call a +1 - 1 compound. Calcium oxide +2 - 2. Product of charges well, +1 times -1 is just -1. +2 times -2 is -4. And so what I'm suggesting to you is that to a first approximation, -3414 is approximately, not quite, 4 times bigger number. I know they're both negative. 4 times bigger number than for sodium fluoride. Not exactly true. I will point out to you that sodium and calcium are diagonal on the periodic table, which means as much as possible, they're as close in size as possible. So we're moving that R term. And then oxygen and fluorine, well, they're next to each other, but they're two of the smallest ions on the periodic table. And there are size effects. That's the next trend we're going to talk about, but we've attempted to remove that part of it as much as possible. Okay. Any questions about this trend? This trend, so we're in chapter 9 right now, finishing up chapter 9. This trend comes back in chapter 11 when we talk about intermolecular forces between ions as well. So, okay. Then let's talk about the next trend. On this other blank slide following that one. And the next trend does deal with size. We'll call this V. For B, crystal lattice energy, delta H CLE, increases as the size of the ions decreases, because size is in the denominator. So crystal lattice energy increases as the size of the ions decreases. And before I give an example of this, I will say that this trend tends to be the bigger trend. And so look at this first. Then, if the product of charges is the same, then look at size. So, note, only consider this trend if product of charges is the same. Because product of charges is a much bigger trend, typically. I mean, they're always both there, but think of, if you've ever worked with instrumentation, this is the coarse adjust, which changes things a lot, and this is the fine adjust, which wiggles things around when you're cruise. Anyway, so as an example of this one, we'll look at sodium chloride, potassium chloride, and cesium chloride. And the delta H CLE, the crystal lattice energies. In kilojoules per mole. Sodium chloride, from the previous example, minus 788. Potassium chloride 70 minus 701, cesium chloride minus 657 kilojoules per mole. All of these, plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. Now let's look at how size plays a role as you go from, well, I'll do it so the ions decrease. As you go towards sodium ion, you get smaller ions, bigger crystal lattice energies. So underneath here. So I guess I should put here, since the chloride ion is always the same, cations get smaller going this way. Cations get smaller, crystal lattice energy gets bigger. Shay, question?
Are there examples where the compounds involved don't have a similar component, like all of these have a chloride? Or are there ways where it doesn't have a chloride, but it's
well, so I think the other example that comes up with the materials that we have on the board would be sodium chloride versus sodium fluoride, where the sodium is constant. And it's true that none of them has to be constant, but as you change things, like on your exam, it will be this clear. Or both of them will get smaller, right? So, because that's the thing about exams, is the questions will be meant, your mileage may vary, meant to be clear and exhibit clear trends. So I guess we could do like lithium fluoride versus sodium chloride, where both of them are smaller, and you say, oh yeah, lithium fluoride will have the, well, I don't know how big actually, but it'll be bigger number, more negative crystallized. Yeah. Good. Any other questions? Yeah, Leo.
What's the relationship where it says equals 1 over 4 pi epsilon naught, and then the key one, Q2 R?
This thing?
Multiplying each other?
Yeah, oh yeah, so those are two terms that are multiplying each other. I separated these constants just because we don't care about them,
Right.
honestly. And we're not using this in any real, like we're not measuring the charges per se or measuring the radii. People do. We're just using this sort of like anybody who has had physics may have seen that, and so we're co-opting any knowledge there. Otherwise, just memorize these trends. And what I really like about this though is we get the product of charge out of it, because that's a nice thing to have. We've seen all along, I mean, I think way back in beginning of chapter 6, I put positive and negative here, and positive and negative here, and I said which one of those is the lower energy configuration. And those two here, this is the lower energy configuration because the charges are closer together, which is again what we're talking about here. And now, what does it mean to be lower energy? It means more negative. It means more negative is lower. Somewhere in my head, it all ties together. Hopefully, it does for you too. Or hopefully, it's a process for sure. Any other questions? Okay. So, I guess let me say one other thing. So, in my attempt to say why we're doing this, crystal lattice energies are estimates of ionic bond strength. Let me write that up. So, delta HCl8 crystal lattice energies are estimates of ionic bond strength. The alternate version of this question, like one question would be sodium chloride or potassium chloride, which one has a larger magnitude crystal lattice energy? You would say sodium chloride because this number is a larger number and negative. The other question I can ask is sodium chloride, potassium chloride, which one has a stronger ionic bond? And you would also answer sodium chloride. And that's what I'm going to write because when we get to chapter 11, that's what I'm going to ask. Which one of these has a stronger ionic bond? And you will have to tell me sodium chloride. Sodium chloride or potassium chloride, which one has a stronger ionic bond? And you will tell me sodium chloride, because that number is bigger and more, therefore more negative. Alicia, question?
To be clear, you consider individual bonds between
Yes.
No double or triple.
No double or triple bonds, and that's because these are ionic.
Oh yeah. That,
Right. So the
No. I mean, each individual cesium and each individual fluorine, one on one, not like CO2.
That's a very good point, because the one example I haven't shown is something like this.
That's 2 bonds.
That it is, but we will only consider the product of charges to be -2 for this, right? I mean, that's the only product of charges I see there, but it's between 1 magnesium and 1 bromide ion. So 2 minus 1 equals -2. That is what I mean for the product of charges of this. And what we would say is that magnesium bromide will have a larger, more negative crystal lattice energy than almost anything that's +1 minus 1. So I don't know if that addresses your question, but that's a very good point to make, and thank you. Somebody's calling me. Somebody outside has a question? Anyway, okay, so that's the end of chapter 9. I think so. Let's double check. Yep, that's the end of chapter 9. And we're moving up to the big board for chapter 10. Oop. There we go. It's okay if I erase all this? Okay, so now it's time to talk about shapes of molecules. To do that, we're going to use something called valence shell electron pair repulsion theory, which basically says that all the electrons want to get all of the bonded electrons, and electrons in general, but specifically the bonded pairs of electrons want to be as far apart from each other as possible. Now, in valence shell electron repulsion theory, at least the way I do it, I refer to something called an electron group. One electron group is any of these things, a single bond, B, one electron group is a double bond, C, a triple bond, or D, a lone pair of electrons. And a lone pair of electrons, those are the electron pairs that are not parts of bonds. Sometimes they're also called non-bonding pairs of electrons. Whatever, they're not dashes, let's say that. They are 2 dots. And so we're going to develop what this means along with valence bond theory. Valence bond theory says a covalent bond forms due to the overlap of one atomic orbital from each of the 2 bonded atoms. And what we're going to be able to do is we're going to look at each of the atoms, put them together, form bonds through overlap of orbitals. Atomic orbitals hybridize. What does hybridize mean? That's a rhetorical question. They mathematically recombine into new orbitals to lower the energy of the molecule. Don't worry, I will show you exactly what I mean by that. And we're going to these are the 2 bonding theories in chapter 10. We're going to develop them together, because I think instead of developing them separately. Good? Questions about this? How many people have done Vesper theory and shapes of molecules before? Excellent. And like so many things in Chem 400, we'll start, I think, with what you've already done and then extend it for Chem 400.
Sorry.
Question? Yeah.
What exactly is a lone pair?
What exactly is a lone pair? Well, if I were to draw a Lewis structure,
I know it's dots. It represents extra electron just hovering in that spot, or how do I do it?
that's the question we're going to answer. So we know how to do Lewis structures at this point, or at least that's where we're hopefully. And then the question is, okay, now we know that this oxygen has an octet. We know that 2 pairs of electrons are shared with the carbon. We know that 2 pairs of electrons are not shared.
And that includes the geometry of the molecule.
They're going to be related to the geometry exactly. And then the question is, where are they? What orbitals are they in? And we're going to be able to answer that question now.
Getting ahead of myself.
You're actually right on time. We're actually about to start answering that with the next slide. But as anything, it'll be a bit of a story. And I would suggest it has a happy ending, but we'll see. It's certainly not a romance, if that's what you're looking for. Okay, so the way I present this is that for each number of electron groups, there are 3 things that are always true for that. Best to memorize them, if you haven't already. So I'll do A right here. 2 electron groups around the central atom. The electron geometry will be, as you probably already know, linear. Bond angle, well, 2 electron groups around the central atom being as far apart as possible, the bond angle will be 180 degrees. Hybridization. Well, you may or may not have talked about hybridization in Chem 300, but that one of the key things will be that however many electron groups there are, that's how many hybridized orbitals there will be. So, and it always starts with S. So that's 1 orbital. We have 2 electron groups, so we need 2 hybridized orbitals. The next orbital is going to be a P. So this is going to be what's called sp hybridization, and we will show you what that means. And to do that, all right, okay, good. All right, now, last time I said that we would see beryllium again. Beryllium is an exception to the octet rule. This is the only time we see it, but it does a really nice example for 2 electron groups. I'll do my Lewis structure down here for beryllium hydride. So simple. I know beryllium doesn't have an octet, and again, we don't have to remember that, but it does form a nice version for this example. Now here's what I'm going to do up here. I'm going to do what's called the beryllium atom unhybridized, which just means it's a beryllium atom. And then I'm going to do the beryllium atom hybridized. The beryllium atom by itself has the same electron configuration we've done for beryllium atoms all along. Beryllium, 4 electrons, 1s2, 2s2. Same place we've always been. So, like so. So nothing new there. Certainly not anything up this sleeve. We'll draw what's called the orbital energy diagram. That's the one with the little boxes. Maybe there's one thing up my sleeve, which is I am going to put in the 2p sublevel. It's empty. It always exists, though, and it is the next lowest energy level. 3s would be after that, but we won't include that. All right, 1s, 2, that's an up and a down. 2s2, that's an up and a down as well. Spin quantum numbers of plus F, minus F, plus F, minus F. All right. Now, I told you the hybridization. The only tricky thing sometimes is that when you hybridize, you know that this has to have 2 electron groups and 2 bonds. And the beryllium will have 1 electron in each of the bonding orbitals. Beryllium has 1 electron in each of the bonding orbitals. And the bonding orbitals are the hybridized orbitals. Okay. Now, told you it's a story. Story's not done yet. The valence electrons are in 2s. And it's the valence electrons that are the bonding electrons. So when I do my orbital energy diagram for this beryllium hybridized, the 1s stays the same. Blah, 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 blah. That's the same. So make that the same. Now it's time to hybridize. I feel like that guy in the double slit video. I should press a button so that we could hybridize now. Now it's time to get hybridized. See that S and see that p orbital I just circled? I know to do that because I know it's sp hybridization. And next step, when I have these 2 hybridized orbitals, one's higher in energy than the other, so when I hybridize, when I mathematically recombine them, they meet at an average energy. So whatever you do draw these 2 as, put the sp hybrid orbitals at the average of them, halfway between them. And I've circled 2 orbitals, and I've circled 2 electrons. So I will now draw 2 orbitals, and I will draw 2 electrons, 1 in each. Okay. I didn't circle these 2. They don't hybridize. They stay the same. And they're still empty. And so I've now just redrawn the hybridized beryllium atom. These 2 are supposed to be at the average here. Let me see. Something like that. Any questions about this? Okay, because so what we get so far is that each of these has 1 electron. Each hydrogen has 1 electron. Those are the electrons that are bonding. Excuse me. I have a question for you. How in the world does this make sense? Right? Did you notice what happened to the energy of those electrons when they hybridized? Did it go up or down? What? What the? It went up? That's not what electrons like to do. Okay. Don't panic. It went up, it's true, but this is before it bonds. When it bonds, and we've shown a picture of what the bonding looks like, as it comes closer to the hydrogen, the 2 atoms lower their energy when they form the bond. So, yes, it's true, hybridization raises the energy of the electrons, but bonding overall lowers them. Maybe it is a romance, right? Bonding is happening. They're getting together, if you will. Anyway, so that's a minor point there, is they go up to form the hybridized orbitals for beryllium. They go down when they form the bonds. There was that. Okay, well, let me leave that up there while I change the slide, because we have more pictures of this. There we go. What do the hybridized orbitals look like? So here's a 2s. Here's one of the two p's. It doesn't matter. We've drawn the z-axis along the left, right. You mathematically combine them, which is what you do with orbitals. Question or something?
So I thought the energy levels were supposed to be quantized. So I'm still trying to figure out what this SD means.
You thought the energy levels were quantized. So meaning that inside a beryllium atom, there was an orbital that had a 90% probability of finding the electron, all true, right? And that this orbital had 2 electrons in it, and this orbital had no electrons in it. And now I'm saying, what are these things that each have 1 electron in? Is that sort of your question, is what happened?
Yeah.
It's a good question. So what they did was they said, well, let's take these 2 orbitals and reshape them into these 2 orbitals because we have to, okay? And the reason we have to is if an s orbital, well, first of all, an s orbital is full of electrons and this one has no electrons. So that doesn't make sense for bonding. Bonding says beryllium gives 1 electron to each bond. Okay? So we ran into a problem with that. Then the next problem is, okay, if it was actually bonding to these 2, then how do the electrons, or how do some of the electrons get up there? And these 2 are at 90 degrees to each other. But the shape of the molecule is like this. So the atomic orbitals, the orbitals of the atom itself, are nowhere near explaining what happens in the bonding molecule. So that's why they're like, well, it's like quantum theory. Well, whatever I was doing wasn't working when I assumed that the electron didn't go into the nucleus. Let's assume it doesn't and see what happens. Well, let's assume that these 2 are at 180 degrees and figure out a theory that, or a hypothesis as to how that can happen. And the best hypothesis is recombine the atomic orbitals that we know and look like this into higher energy hybrid orbitals. Crap, that doesn't sound right. Oh, the molecule bonded does have lower energy. We're saved. So yes, they took these orbitals and recombined them into these orbitals. And this process, by the way, is what we will end up calling constructive interference and destructive interference. 2 orbitals combine. This is a positive and a negative part. Anyway, we won't quite talk about that yet. But they're recombining into these orbitals, which we typically draw like this. So these are pictures of hybridized orbitals, and that's where we're going. So I don't know if that answers your question, or also creates more questions. But the energy of the electrons still is quantized in these different shapes. Yeah. So, yeah, that's the best answer. I mean, I think what's going to happen is that when you do a theory, when you do science, it's not always good to say, I know what the answer is, so let's come up with a theory that works, unless it predicts other molecules, and this one did. So that's why this works. Okay, so I have 2 things here on this slide that I haven't done yet. I have to draw the shape of BeCl2, and I have to define a sigma bond. Well, the shape is pretty easy because it's just 180 degrees. What I'm going to do, instead of drawing the shape, I'm going to draw what's called an orbital overlap diagram. And I can't quite write on my wall, so I'm going to do it down here. Draw an orbital overlap diagram. That's what's taking the place of draw the shape. And an orbital overlap diagram, as you might guess, shows orbitals overlapping. So there's my beryllium, and there's its orbitals. And here's the crazy thing. I'm attempting to draw this now. And I won't draw the up and down arrow, but I will draw an electron in there. And that's beryllium. And this one lobe is one sp hybridized orbital. And where's my pointer finger? Here's my pointer finger. So you see this thing right here? It is that. And technically, there's another smaller blip of opposite phase that we are not drawing. And you see this right here? That's this big blue part here. So this is another sp hybridized orbital. And brilliantly, this is what's really up my sleeve, their angle between those two blue parts there is 180 degrees, which is exactly what's observed. Does anybody see my red pen? Ah, that's good. Now it's time to draw in the hydrogen. And the size won't matter. I know hydrogen's pretty small. I know it's a 1s orbital, but I'm just going to draw it. What's the shape of a 1s orbital? Spherical. I'm going to draw it as a circle. And I'm going to label it 1s. And that is an orbital overlap diagram. Well, it's not quite done. Let me do the other one. That is an orbital overlap diagram for beryllium hydride, beryllium dihydride probably, showing the sp hybridized orbital overlapping with the 1s orbital of hydrogen. One down. Questions about this currently? Because we get to do it again. And then again. Well, now we go to 3 electron groups. All right. For 3 electron groups, the electron geometry is trigonal planar. Called trigonal planar because all 3 of the bonded atoms go in the flat plane of a surface, such as the board. Bond angle 120 degrees. Hybridization, well, 3 electron groups, 3 hybridized orbitals. Always starts with the S. It's called sp2 hybridization. I know that's confusing because the 2 is usually the place where we put the number of electrons. Not so in this case. That means 2 of the p orbitals are hybridized. Total of 3 orbitals hybridized. The example we're going to do is Bf3. Boron only wants 3 pairs of electrons. Fluorine wants an octet, so it will get its octet. Now remember, when I draw these Lewis structures, it's because we've done all the rules for drawing Lewis structures. We've counted up valence electrons. We've put the least electronegative atom in the center. We've sprinkled all of our electrons to get octets, and we end up here. Because you cannot do this unless you can automatically do the Lewis structure. Then we do this. All right. Boron atom. 1s2, 2s2, 2p1. That's a total of 5 electrons. Draw the orbital energy diagram again. Same thing as before, except we get one more electron. One of the electrons in 2p. One s untouched in the hybridized boron atom. Okay. It's sp2 hybridization. I want one electron in each of the 3 orbitals that I circled. Choose those 3 orbitals, 3 electrons, 3 bonds. Three orbitals, 3 electrons, 3 bonds is what we want to end up with. I have 2 of my p's. I have 1 of my s's. Technically, it should be 2/3 towards the p's because I'm taking 2 of the p orbitals. As long as it's between them, I'm okay. And as long as the P is clearly somewhat higher in energy, that's what I'm looking for. 1 electron in each of those 3. I am bleeding. It's okay, I'll survive. And so that one's. Let's see, we got the Lewis structure, we got boron atom hybridized. Questions about this? All right. Then we'll go to the next slide. Now we have 3 hybridized orbitals. We say 2s, any 2 of the 2 p's. If you look at those 3 orbitals and you squint really hard and overlap them, maybe you can imagine they form this. I don't know. It does happen. This is what happens. We get orbitals that look like this. This time we will draw the shape. Then we will draw an orbital overlap diagram for this molecule. I'll draw the shape first. Remember, Lewis structures don't have to show shape. They can, they don't have to. Now that we know there are 3 electron groups, bond angles 120 degrees. You don't have to draw those 120 degrees. As long as I get the idea that it's triangular, it's planar, and they're about 120 degrees. No protractors will be provided on the exam. Don't bring your own. All right. So that's all it means by the shape. Shapes don't have to have all the electrons. They can, though. Lewis structures have to have all the electrons, but they don't have to show shape. Now let's draw an orbital overlap diagram for boron. So those are supposed to be those 3 orbitals up there. They're at 120 degrees. They look like balloons. They each have 1 electron in them. Now let's do the fluorines. For fluorine, what orbital has one electron in it and is ready to bond? It's in the 2p area, 2p5, one of those p orbitals, right? Hydrogen, it was 1s that bonded. This one's going to be 2p. So draw something like a 2p. No hybridization necessary for fluorine. So, I don't know. I'm kind of out of space, but I'll do it anyway. There's my 2p. Fluorine has one electron that goes back and forth in here. Anyway, there's the electron forming the bond. And now I will do that 3 times. And hybridized sp, sp2, etc. orbitals just have one area that you draw, typically. But it's still a p orbital, so you still draw the 2 parts of it for fluorine. Questions about this? Four electron groups around the central atom. As they say these days, rinse and repeat. Without hurting myself again. All right, keep that up for a minute. For 4 electron groups, does anybody know what the electron geometry is?
Tetrahedral.
It is tetrahedral. Bond angle for tetrahedral, anybody? 109.5 degrees. 4 electron groups, 4 hybridized orbitals, sp3 hybridization. sp3 orbitals. All right. Time to erase that. Example is going to be methane, CH4. Surely it has 4 electron groups. Another molecule that has 4 electron groups around the central atom. Water, H2O. But we're doing methane right now. Carbon atom. 6 electrons total, 4 valence electrons. Need a little stamp that does this. So that's just plain old carbon. And in a lot of ways, like I like processes. And so if you remember when we did electron configurations of ions, I always did the atom first and then took off from there to do my ion. In this case, whenever I think of the orbital energy diagram for something that's hybridized, I always do the atom first and then think about what's next. Here, I have 4 orbitals, 4 electron groups, 4 hybridized orbitals, 4 electrons. 4 orbitals, 4 electrons. Note, it's sp3 hybridization, and I'm circling the s and 3 of the p's. So there's hints all around. 3 of the p's and the s, it's going to be very close to the energy of the p's, 3/4 of the way towards it. And have all 4 of those orbitals my lonely 1s. And my sp3 hybridized. Okay. 4. 1, 2, 3, 4 orbitals. 1, 2, 3, 4 electrons. Any questions about that? Okay. Stephen.
That one, so is the 2p essentially like, it's not there because we use the sp3?
All my P's have been hybridized. Right, exactly.
So you're basically making an entire new orbital level.
Yes, an entirely new hybridized set of orbitals.
Okay. So the 2s and 2p no longer exist with this.
The 2s and 2b's no longer exist. They are now the sp3 orbitals. Nice. Bodhi?
What's the probability of finding the electrons in these hybridized orbitals? It's still 90%.
And so yeah, what's the probability? Still 90% for these shapes. Yeah, no, that's all part of this hybridization process. It's still using the same definitions, knowing what the shape is, and then recalculating these shapes for the bonded out. Question? Jeff?
What's the 3, the sp3?
This 3 means 3 hybridized p orbitals. I know, it doesn't mean 3 electrons. I don't make up the notation. It means hybridize the s and all of 3 of the p orbitals. Any other questions? Because, by the way, this is the most important example because everything has carbon almost, and therefore almost everything is sp3 hybridized. There will be some exceptions. Well, we still have some time left, so let's keep going. All right. This is my favorite part. So, draw the shape of CH4. CH4 is not planar. It is a 3-dimensional molecule. In my Chem 400, there is one way to draw it. If you want any points. If you want 0 points, draw it however you want. For all tetrahedral central atoms, there are 2 positions that are flat in the plane of the board. That's these 2. And these 2 lines are lines. But this line is coming out towards you, so it's getting bigger. It's a sense of forced perspective, and it's certainly not an art class, but the line gets bigger. It's sort of, in movies, when things get closer to you, they get louder. It's the same idea. And so this is called an out wedge. And this dashed line is called a back wedge. And I don't know if you can see it in the back there, but it looks like this. And it is angled down. So, do you know how many points you get for this drawing of tetrahedral? 0. Yeah. Do you know how many points you get for this drawing of tetrahedral?
0.
0, thank you. Are you getting the idea? Okay. Do you know how many points you get for this drawing?
All of them.
All of them. Usually 6. Could be 10. Right? And if you do this drawing, you know what I write on your paper on the final? Minus 1,000. But then it's really only minus 6. No, I don't like that. Anyway, and if your question is, Are you insane? Perhaps. But my idea is that you have to get used to three-dimensional drawings on two-dimensional paper. And this is the way you're going to have to do it in my class. In all other classes, it might be slightly different, but you will have this as a basis. And because out wedges and back wedges are on, even on the pharmaceutical, like when I open up my Flonase, there are out and back wedges on whatever the molecule for Flonase is. That's how important shape is for organic chemistry and biology molecules for sure. So, anyway, now I'll actually draw it with the hydrogens on it. Something like that. That would be a complete shape picture of that. Brenna?
Does the out wedge have to be facing down?
Does the out wedge have to be facing down? Yes. And so if you were to draw a line through the center of the carbon, 3 of them would be angled down. I guess all 3, and 1 of them would be straight up. So all 3 of them have to be angled down, and this one has to be straight up. Is there a song called Straight Up? Paul Abdul, maybe. I don't know. So yes, so good to ask questions about it. That's a good one. So really, how many points would you expect for that? 0. Check.
Why is it in this one, this is the only one that we're not actually drawing orbitals, we don't have hybridization, just have lines?
Oh, I'm sorry. So we can still do what's called an orbital overlap diagram for this too. This is the first shape, though, that is three-dimensional. Now, if I do an orbital overlap diagram, like with the big circles for the hybridized orbitals, don't have to do shape for that. Right? The primary thing I'm looking for is that when you do it, and we can do that now. So, see. All right, that's how I would draw a carbon. Now I still draw it in approximately the same shape, but I am not nearly as anal retentive about shape for that one. But when it says draw the shape of something that is tetrahedral, that's what I mean. But for orbital overlap diagram, it can look something like this. And then these are hydrogens that bond with their 1s's. So label each of those as 1s. Because the one thing about what are called orbital overlap diagrams that show the actual orbitals overlapping is each orbital must be labeled with what it is. Any other questions about this? Jeff?
The bond angle is 109.5, but which angle is that?
Bond angle is 109.5. Is that what your question is about?
Yeah.
This is 109.5. This is 109.5. The angle between these two, Can I demonstrate tetrahedral? See this one? That's the one coming out at you. And these two are flat, and one comes out and one goes back. I cannot actually, I don't think I can draw that particular orientation. Well, let's see. Anyway, so yes, each of those, the angles don't add up to 360 because there's a three-dimensional aspect. Any other questions? Tomorrow, Wednesday, oh, sorry, Leo, one.
Yeah, just real quick, would it technically be correct to draw one line down and then 3 up, like, inverted?
It's always one in every group. You mean would you get credit for this?
Yeah.
I don't know.
Technically, if you flip the paper upside down, it's still right.
It's a 6-point gamble on your part. Since I've said there's one way you will get credits.
So I get 9 points.
What's that?
So I get 9 points.
Because it's upside down, you'll get 9 points. Yes. I don't know. Or you get 0 or upside down 0, which is easier. Probably you're fine, but because it embodies the heart of what I'm talking about. I don't know why you would do that unless you're a contrarian. I was at this meeting last night where everybody voted yes and one person voted no just because nobody else voted no. That's fine. We humored him. I will humor you. No, it's all good. Wednesday, we've done 2, 3, and 4 electron groups. What's additionally special about Chem 400 is we do 5 and 6 electron groups on Wednesday, and then we go from there. That's it for today.